My name is Julian Mestre. I'm from the University of Sydney. This is joint work with Riccardo Collini Baldeschi and Oke Schravers from Facebook and Chris Wilkins from Tremor Technologies. The title of the paper is The Ad Types Problem, and it's a new framework for online advertising in the context of user-generated feeds. So I don't need to tell you that online advertising is what powers the internet. And we have three examples here. Your typical Google search ads, where you have a couple of slots here at the top of the search results, and then the search results afterwards. This is just a query for kitchen renovation. And this is a Pinterest feed, also for the same keywords, where you have pin boards, and interspread with that, you have paid ads. So there's one here and there's one there. And this is my Facebook feed. Between posts of dogs and whatnot, you also see recommendations for kitchen, in this case, in general, home renovations. So I didn't search for this particularly, but I guess Facebook knows what I'm looking for these days. And it showed me an ad for some paints. Anyway, okay. So sponsor search ads typically then. The setup is you have a small number of ads that are shown next to organic search results. Are homogeneous, they all have one little slot, and the top slots are more valuable than the slots further down the line due to the higher click-through rate of the top ads. So the way this is typically modeled is you have a position auction model where each slot has a discount factor alpha j. So j goes from slot number 1 all the way to whatever number of slots you have. And each ad has a value vi, which takes into account the quality of the ad, like what is the probability that a user is going to click on the ad, and the value that this ad has for the advertiser. So it captures all that. And what we want to do is we want to find an allocation sigma that assigns for each slot j, an ad. And typically the objective that we want to maximize is maximum social welfare. And so for every slot j, we multiply the discount factor of that ad, of that slot, sorry, and the value of the ad that was assigned to that slot. In the ad types problem, this is a framework that we are proposing in this paper. It's a little bit different. We have large number of slots, not just a few, and they're interspread with organic content that comes from a fee that essentially doesn't have an end. It goes on forever. So I should be able to keep on populating ads as I scroll down the feed. Ads usually in this context have different types. So we have text ads, which just have a little snippet of text, but we also have richer ads like text with a picture or text with a video. We also have organic ads that promote features of the platform or public service calls for action, or to bring awareness of things that are going on, etc., etc. So there are different types of ads. And we want to have at the top, which are the profitable slots, right? So those are the ones that people are going to click through most likely. But we want them spaced throughout the feed. So this is the model that we are proposing. We have, like in the previous case, ads in addition to the value that is intrinsic to the ad has a type. And then for each type, we will have a discount curve, alpha 1, alpha 2, all the way to the number of slots that we're interested in populating. That will tell me what discount factor should I apply to showing this ad on this slot. And then the last the last ingredient of the model is a gap matrix, which specifies the minimum distance between two ads of a given type. So for two ad types, I will have a number that tells me if I show this ad type here, I need to let these many slots go through until I can show the ad of this other type. Yeah, so the ads are nicely spaced out throughout the feed. Right. So, for example, if I showed a video, maybe I don't want to show another video right away because videos take more bandwidth. So I want to space them out more than other things. If I show an organic ad where, say, I remind the user of something cool they've done in the platform, those are very positive ads, so it's okay maybe to show a real ad after that. So I don't want to leave so much space between those two, etc., etc. Okay, so beyond our contribution of defining this interesting model for online advertising, our algorithmic contributions are as follows. We have an algorithm for finding the maximum welfare allocation in n squared times k plus log n time. Remember, n is the total number of slots that we have, and k is the number of ad types. So typically, k would be smaller than log n. And we also have a way of computing VCG prices in the same time. Both these results apply to the case where we don't have gaps. So we have different types, and each one has different discount factors. But they don't have ads. So in this case, for example, this captures even spacing, right? So if I say exactly every 10 slots, well, I can forget about everything that is in between and just focus on those. And then we have the case with gaps, where the matrix can be completely arbitrary. And for those cases, we show that there is no k to the 1 minus epsilon approximation for any epsilon unless p equals np. And we have a dynamic programming based algorithm that runs in k times n to the 2k plus 1. All right, so those are our contributions. In today's talk, I'm mostly going to be focusing on the algorithm. I would like to give you a sense of the techniques we use and the main ideas that allow us to get this algorithm. And then I'll quickly skim through in more detail these statements. All right, so our algorithm is going to be based on the Hungarian algorithm for finding a maximum weight matching in a bipartite graph. Okay, so this is the first thing we need to understand, that when there are no gaps, this is just a maximum weight matching problem. So this is an LP for our problem. We have a variable x ij, which means add I is shown on slot j. And then we say that for all slots, I want to show at most one ad. And for every ad, I want to show this ad in at most one slot. I don't want to show the same ad twice. And then our objective is to maximize the weight of the assignment, which I take these indicator variables and multiply them by Vij, which takes into account both the discount factor of the slot j for this type of ad and the intrinsic value of the ad. Yeah? So basically, that's what it is. And this is the dual solution. So in the Hungarian algorithm, what happens is that we start with a trivial dual feasible solution that has very high cost, but it's feasible. And we have a feasible integral solution that it's not optimal. And what we do is we try to bring these two together by decreasing the value of the dual and increasing the value of the primal solution. And as we go along, we keep a couple of invariants, and one of them is that all the non-zero entries in the primal solution, all the edges I'm picking in my assignment, are tight in the dual. So there's equality here for that corresponding edge. So the algorithm works in phases. So in each phase, we update the dual solution by reducing its value. Remember, the dual wants to minimize. And then at the end of the phase, we are able to grow the primal solution by 1. So eventually, since I don't remove things from the, I don't decrease the size of the optimal solution, I will have matched everyone that is there to be matched. And the property is that at the end of the algorithm, the value of the primal and the dual are equal. And therefore, we have an optimal primal solution. Okay. So in one of these phases, the algorithm does the following. It looks at this set of tight edges in the dual solution that we currently have, and it builds an alternating tree out of the free vertices in V. If this alternating tree has an augmenting path, then great. We can use that to increase the size of our matching, and that ends the phase. But if there is no such augmenting path, then we can find this other structure that allows us to decrease the value of the dual solution until one more edge becomes tight, in which case we can keep growing the tree, and eventually we are bound to find an alternating path and an augmenting path, and then the phase will end. All this work can be done, and you just need to believe me, in order E plus V log V time. Right. So let's see what that means. Let's see how that works in a pictorial fashion. So I have my free vertices, and I start growing the alternating tree by looking at unmatched edges. If one of these guys is unmatched, well, I have an alternating path, and I can increase the size of the matching. Otherwise, these guys are matched, and I go to their neighbors, and I repeat the process. Right? If at some point I do find an alternating path of free edges, these are the orange ones, and matched edges, these are the black ones, then I can flip this orange with the black, and now I have a bigger matching. If that's not the case, then what I do is I decrease the value of all the odd layers in this alternating tree, and then I increase the value of the dual solutions in the even layers. Because I have more odd nodes than even nodes, I'm bound to decrease the value of the optimal solution, of the dual solution, excuse me. Now, because all these tight edges that I'm looking here, one of the endpoints goes up and the other one goes down, I'm not changing the status of those edges. But there may be some edge outside that I'm decreasing this endpoint and I'm not increasing this endpoint. And therefore, at some point, that edge, the dual constraint, may become tight. In which case, we add it to the Hungarian tree, and now we keep growing our tree or find an alternating path. Right? So we can do all this stuff if we can keep the track of the slack of these non-tight edges. That's basically all we have to do. And it can be done using a priority queue with E of the priority operations and V, delete mean operations. So if we use a Fibonacci queue, this is the running time. Okay, so each phase takes E plus V log V, and there are M star phases. Let's say that's the size of the assignment at the end. So in our application, we have these are the number of ads. We have K types, and we have N ads for each type. These are the number of slots N. So therefore, E, the number of edges, is the product of these two, and M, the size of the maximum matching, is N. So plugging all these things together in what I said before, we get a running time of K N cubed. Right. So If we want to improve this running time, then we need to maybe use a different algorithm, or at least use the structure of the edge weights, which in our case, there's a lot of structure out there. So for example, if we only have one add type, then simple greedy algorithm solves this problem optimally. That's not the case here. The different adds types complicate things, but there's still a lot of structure that we can use, and that's what we try to do. And this is the key insight that we had for solving this problem. We came up with this uncrossing lemma, which says the following. If we have two adds, I and I prime, of the same type, and two slots, j and j prime, say the value of I is higher than the value of I prime, and the discount factor of j is greater than the discount factor of j prime. So remember that the smaller the discount factor, the more we are penalizing that slot. So that's further down the list. Then the statement is that in any feasible dual solution, we cannot have both of these edges be tight. I to j prime and I prime to j. So this is kind of, they would look like this. They would be crossing. Yeah? So that's why we call it the uncrossing lemma. So any other configuration is fine. So we can have I match to j and I prime match to j prime, or I match, not matched. So these are tight edges, or I having tight edges to both j and j prime, or the other way around. One of the guys having tight edges there. That's all good. But we are not allowed to have the first configuration. So this one is no good, and any other configuration is fine. So as long as we don't have that cross, we are happy. Otherwise, the solution cannot be feasible. And the argument for this is not very difficult. It follows from the fact that that these are the discount factors are done in this way, that the weight is the multiplication essentially of these two values. All right, so how can we use that? Well, in a phase of the Hungarian algorithm, we can ask the question, what are the edges that we need to keep track of? Remember, before we had to keep track of the slack of all the non-tight edges. And now say I have these adds for a given type, and I have these slots. And right now, these are the matched edges. Okay, so these three adds from this type class are matched to slot number 1, 3, and 5. Oh. Okie dokie. So the claim is that this edge will never become tight. Why? Because the updates that we do preserve tightness of the edges. So whatever we do down the line, this edge will always stay tight. And therefore, by the uncrossing lemma, we don't need to look at this edge here, because that would violate the fact that the dual solution that we keep is always feasible. What about those edges? Yeah, we need to take a look at those edges, right? So we need to keep track of that. But you see that for every slot here on the right, there are essentially two places that I need to keep track of, right? So this guy will fall between two of these add types, and I have to keep track of those two edges. For everything that comes after here, I only need to keep track of the edge going from here to the last matched add and the first non-matched add. So it's the same story. So that means that, and this was for one add type, I need to multiply by k because I have k add types. So therefore, I only need to do k times v update priority operations and v delete min operations still. So the running time is a little bit better. and it works out to n squared k plus log k. So we're setting a factor of n. And remember, this n is the number of slots. In our application, the number of slots is large, typically. So what can we do beyond this? Well, we can also compute the VCG prices in the same time. This also holds for the case without gaps. What if we throw gaps in there? Well, the problem becomes significantly harder. So what we can show is that there is no k to the 1 minus epsilon approximation for any epsilon, unless p equals np, even when there are no discount curves, right? You just have add types, and there is a very complicated gap matrix, and k is part of the input too. So we have lots of add types. And then we have a DP-based algorithm that runs in k to the n to the 2k plus 1. All right. So what are the open problems? Here, there are quite a few, and it's mainly in the area with gaps. For the problem of welfare maximization without gaps, we have an argument that shows that probably this is the best you can do, because there is a way of coming up with to reducing a regular assignment problem to this problem by increasing the size of the graph by a factor of n. So basically, we are not losing much there. Then the interesting bit comes from the case with gaps, and here there are lots of problems. So what are the properties that make this gap matrix a tractable problem, right? So like I said before, if the gap matrix is all uniform, say some number 10, right, for all add types, then, well, that can be reduced to the case without gaps. So we can solve that problem. Are there any other tractable classes of gap matrices that we can define? And what are the properties of the gap matrix that makes the problem FPT? So right now we have an algorithm that runs in n to the 2k plus 1 for the gap case. That's not quite fixed parameter tractable. Ideally, we would like to have the running time that depends on k in a nasty way separate from the size n of the instance. So what are the properties there? And what are the properties that make for that allow good approximation algorithms? If we bound the values of these gaps, can we say something there? And finally, what if the gap constraints are not hard? So maybe there is a penalty that we can add to the objective value, and we can get something interesting there. All right, so those are the open problems. Let me just recap very quickly, and I'll wrap up. Our main contribution is that we introduce this add types problem, which captures the setting where you have a large number of ads interspread with organic content. We have different add types, and then they have to be, they cannot be all bunched up together. They have to be gaps between the ads. We give a solid first theoretical treatment, but I believe that there are lots of interesting problems there left to explore. And with that, I would like to finish my talk. Thank you.